Alright guys, this is the second take on this one. Before we move on to Faraday's law, we need to define a few things that deal with magnetic flux. So, our definition of magnetic flux, the way you want to think of it, is that first of all, it's a pretty abstract concept in the sense that Michael Faraday, the guy who the law was named after, we're going to be talking about in a little bit, he came up with this idea of a field to help describe the intensity of various influences, whether they were electrical or magnetic. And a field is just our way of drawing these lines of influence and showing that where these lines are closer, the field is stronger. That immediately tells us that the number of field lines is directly connected to the strength of the magnetic field. Now, we're not actually counting field lines, okay? It's just a way of thinking of this. But to think of the amount of magnetic influence due to a magnetic field, you can imagine that this concept magnetic flux is just the number of field lines present, okay? So the symbol is phi, or phi, the Greek letter. The units are Weber, all right, which is the same as saying Tesla times meter squared. I'm going to explain that one in a second here. So where that comes from is this concept of magnetic flux density, which is to the right there. Now, anytime we talk about the intensity or strength, okay, or density, we're talking about some number of something per unit area or unit volume. In this case, what we're looking at is the number of field lines per unit area, all right? How many Weber, if you want to think of Weber as just a way of saying number of field lines, all right, per meter squared. That unit right there, that's the Tesla. That's what we've been dealing with, that magnetic field strength. The symbol for that's B. All right, so we've already done a little bit of work with that. You sort of have a physical intuition built up about that. So the formula for that is for magnetic field strength is the number of field lines per area, phi over A. And so if we solve for the number of field lines, it's just the strength of the magnetic field times the area we are considering. This is important when we start talking about electromagnetic induction and Faraday's law, because we care about counting those total number of field lines. Now, when we deal with these field lines, in the previous image you saw that they were all perpendicular to the surface that we were considering. What if they're not? Well, if they're not, we need to consider the component of the magnetic field that is perpendicular through the surface, A. And what we see here in this drawing right here, right, we have our magnetic field line, B, right, and it's not perpendicular to A, and it makes an angle of theta, we'll call it, and rewrite this here when you reuse phi, okay, with the normal to that surface. And the normal is another word of saying the perpendicular line to that surface. So we want that component, we want to know how much of that B, all right, is perpendicular to that surface. That amount will be the full amount of influence felt through that area, okay, that full amount of magnetic influence. That's what we care about. So to solve for the total amount of magnetic influence, all right, the number of Weber, we got the magnetic field strength times the area through which it passes times the cosine of the angle between the magnetic field and the normal to the area. We care about the normal here, okay? When you get into this later, it's cross product. Okay, the cool thing about this is that if you combine these areas, if you overlap them, okay, and consider all these areas together, you can compound, all right, the amount of magnetic influence felt through a certain region. So in other words, what I'm trying to say here is that oftentimes in electromagnetism, the area we're dealing with is the area through a coil of wire. Okay? So right here we have a single coil of wire. Within that coil of wire, we have a certain area. What typically happens is that coil of wire isn't just one loop. It is multiple loops. Okay? And all of these multiple loops are linked together. Linking all those loops together has the effect of increasing the total magnetic influence through all of those loops. So what we have is something called magnetic flux linkage. Okay? And it's basically the product of the magnetic flux through a coil of wire, which is phi, times the number of turns in that wire. So the magnetic flux linkage is this term, this N times phi. Okay, that is the magnetic flux linkage, which is just taking the above formula and multiplying both sides by the number of loops in the coil, giving us the total influence felt by that coil of wire. Very important when we start talking about generators. So like I said before, we care about the amount of magnetic field that is perpendicular to the area we're considering. If we consider the angle to be the angle between the magnetic field and the normal to that area, so in other words here we have this dashed line drawn down the middle here, we have our magnetic field lines coming through, and our coil, all right, of wire is perpendicular there. All right, so we see that the angle between the normal and the magnetic field lines here is 0 degrees. We're told that the coil has a cross-sectional area of 0.50 meters squared, N equals 50, and the magnetic field strength is 0.20 Tesla. When we solve for the magnetic flux linkage, all right, N times phi, well, we just need to do N times B times A times cos of theta, all right? And we put this all together, it's just going to be 50 turns times 0.20 Tesla times 0.050 meters squared, and we end up, times cosine of 0 degrees, all right? And what we end up with here is 0.10 Weber, okay? Do the same thing for the next two examples here. B, I believe, is at a 50-degree angle. I think it was at a 60-degree angle. It looks like 60 to me. Okay. So what that says right there, all right, is that at a 60-degree angle, the area, the normal, is 60 degrees to the magnetic field line. So theta is equal to 60 here. We're going to solve for that flux linkage. When we do that, we should end up with 0.050 Weber. Okay, C. Well, since the normal is perpendicular to the magnetic field lines, it is 0. And that makes sense here, because look, the magnetic field's not passing through the area that we care about, okay? It's passing between the wires, but again, that's normal, all right, to the region of influence that we're talking about. So theta, excuse me, phi, N times phi, in this case, is equal to 0. All right. Next video, we're going to talk about the EMF induced by a time-changing flux.